In this video, we're going to be considering separable first-order ordinary differential equations. So a separable equation is one that has the form dy dx, the derivative, is equal to some function of the independent variable x multiplied by some other function of the dependent variable y. So something of this form is separable because the independent variable x is different or is separate compared to the dependent variable y. And we'll see what that means in terms of how we solve it. So in general, to solve this type of equation, we want to separate the independent and dependent variables. And we want to separate them to the opposite sides of the equation. So in general, this would look like this. We're going to divide both sides by the function of y, keeping the dy on this side, and multiply both sides by the dx. So because this equation was separable and we had g of x and f of y as products, we're able to write something of this form. And the reason why this is then useful is because now we can integrate. We integrate both sides. And so this is going to look something of this form. We have the integral of that function of y, dy, and that would equal the integral of the function of x, g of x, dx. Now this is just a general way of writing this. Now in order to solve an equation specifically, there's two different approaches that can be used. And we'll see both of these approaches in an example. So let's say we have the equation dy dx is equal to y plus 2 divided by x plus 1. And we are also given an initial condition that y, when x is equal to 0, is equal to 1. And in this specific question, we're also giving another piece of information that the range y is always positive, so it's greater or equal to 0. And the domain is also restricted to be greater or equal to 0. Now, when we look at this example here, compared to the general form, we see that the g of x could be considered 1 over x plus 1, and the f of y could be considered y plus 2. And that's now a product of these two. And so now, when we want to separate this, we're going to divide both sides by the y plus 2. And we're going to multiply both sides by the dx, just like we did in the general case. So what we're doing is we're trying to keep all the y's on one side and all the x's on the other side. Now at this point, there's two different ways of how we can go about solving this equation. So the first approach uses an indefinite integral. So for the indefinite integral, what we're doing simply is integrating this as it's written. So we're going to integrate one side with respect to dy, and the other side we're integrating with respect to dx. Now, something that's often useful when we have separable equations is this relationship, which can be summarized as the integral of 1 over a linear equation, so ax plus b, with respect to dx. This is going to be equal to 1 over a times the natural logarithm of the absolute value of ax plus b, and of course the constant. So this relationship is often going to be useful when you have rational functions that are being separated. So back to the indefinite integral, we can now solve the integral on both sides of the equation. So for the first one, we're going to have the natural logarithm of y plus 2 plus some constant. And then on the other side, we're going to have the natural logarithm of x plus 1 plus another constant. Now, because we know that y is always greater or equal to 0, and we know that y is greater or equal to 0, and we know that x is greater or equal to 0, because of that, we can now drop the absolute values because y plus 2 is always going to be positive, and x plus 1 will always also be positive. So we can simply write it like this. Now the other thing to note is that because we have two constants, we can just lump both of these as one constant. So we can call that C3. And now it's simply just a matter of solving this equation for y. So we can raise both sides to the power of e, or rather raise the sides with a base of e. So y plus 2 is equal to e to the power of ln x plus 1 plus c3. Now because we have a sum as the exponent here, we can write this with the same base. So this is multiplied by e to the power of c3. Now something to realize here is if we have the natural logarithm, that is the exponent to an e here, that's going to basically simplify to just x plus 1. And now what we also realize is this e to the c3 is also just another constant, and we can just call that c. So what we have here we can now solve for y. And we'll have something of this form. Now, because we're given the initial condition, we can solve for c. So we know the initial condition is that y0 is equal to 1. So with this, now we go back to our equation and we can say that 1 equals c times 0 plus 1 minus 2. And solving for c, we get 3. And so this means that y is equal to 3 times x plus 1 minus 2. And we can simplify that into the linear equation y is equal to 3x plus 1. And so that is our solution using the indefinite integral approach. Now another way of doing this, which could be easier depending on the specific situation, is using a definite integral. This is the second approach, using a definite integral. So for the definite integral, now we're going to put limits on the integral, so we're bounding it. So like before, we have the integral of 1 over y plus 2 dy is equal to the integral of 1 over x plus 1 dx. Now the integral bounds that we want to use are going to start at the initial condition. So x would be 0, and y would have to be y at 0. That's the initial condition. And we're going to some arbitrary x. And the corresponding y would be that y at that x. So we're always writing the limits so they correspond to each other. The dependent variable should be at the same location as the independent variable. So here we start from 0 to x. So then here we have y at 0 to y of x. Now, of course, we're given that y at 0 is just 1, and y of x is, of course, just y. Now, solving this, we solve it in the integral the same way as before. So the natural logarithm of y plus 2, and now this is bounded from 1 to y. And on the other side, we have the natural logarithm of x plus 1, and that's bounded from 0 to x. Now, like before, we know that it's always going to be a positive, the y plus 2 and the x plus 1, so we can drop the absolute values, and we can evaluate these, the results with the integral bounds. So we'll have the natural logarithm of y plus 2, so that's at the first bound, minus the natural logarithm of, so substituting the 1 for y, so 1 plus 2. And similarly on the other side, now we can simplify this. Now here you might realize immediately that the natural logarithm of 1 is just 0. So that term basically goes away. And so now there's basically, again, we're just trying to isolate for y. So there's lots of different ways we can do this. One of the ways might be to combine the ln of y plus 2 and the ln of 3. Because we're subtracting them, we can write this now as a division. Like this. Now take both sides with a base of e. So we're getting rid of the natural logarithm. And like before, solving for y, we get back the same result that we got with the indefinite integral approach, y equals 3x plus 1, and with the definite integral, we got back to y equals 3x plus 1. So it depends on which one you prefer, which method might be easier for you, but in the end, we get the same result.